Hello everyone, thank you for attending to my talk on lifting 15-ton blocks with Eclipse. I'm Arthur Dossi and I'm working for OBEO. OBEO is a French company really active in the Eclipse community. We are working on several modeling technologies such as Sirius, Axelo, ETH and others. What you need to know about us is that we love Eclipse and EMF. MESURIS, our client on that project, is also a French company which is specialized in bathymetry and conception and installation of electronic systems. What you need to know is that they love the electronics and big machines. So what is bathymetry? Bathymetry is a way to collect data to build a representation of a construction site, in our case a point cloud of a dike. In MESURIS go to the construction site with their boats and, using their own technology, create a representation of the dike and the seabed underneath, which is a really precise point cloud that we're going to use in our software. What kind of data are we talking about? Everybody knows what is a dike, but in our cases we are talking about which are built with this kind of block, really specific bone block, that are used to improve the overall quality of a dike. And the software is about helping lay down those blocks and verifying some constraints afterwards. Last photo, just to be sure we're talking about the same dimension here. Just have a look at the size of the block and the machine, the engine, the crane there, compared to the size of the person on the left, and you will have an idea of the size of the block. Okay, so OBEO contacted us because they wanted to build a software to answer two main requirements. The first one, they wanted to provide to their users, the crane pilots, a live representation of the block being laid down. To do that, we had to build the software with interfacing it with their own system called PosiBlock, which is a gathering of sensors they set up on the crane that could give you enough information so you can compute the exact position and orientation of the block. Using that, we built a live representation of the block. The other part of the project was about providing some analyzing tool on the construction site that could verify some constraints, density, orientation, and stuff like this that are required to verify the quality of the construction. And also provide a way to find or compute the exact position of block from a point cloud. This could be really useful if you want to verify the stability of your dike after, let's say, a storm. After a storm, the block could have moved and you want to verify there is no breach in your dike. So you use this kind of software to do that. So, a short demonstration. Here, the product we've built, it's an Eclipse E4 RCP application. We have three main views. Over there, we have a Project Explorer view, which is a 3D representation of the EMF model. On the bottom left, we have a property view that displays the property of the current selection, and a 3D view here that displays the scene for the crane pilots. Then, when I start a placement here, you can configure that placement using this window. And now we have our live representation of the block here, with this green line, which represents the sling, which is a connection between your block and the crane. Over there, we have live widgets presenting useful information to the user. Using an emulator, I'm going to lay down that block on its target. Here, I'm over the target. Now I'm going to drop it here. Now I'm going to say to the software, okay, I want to release the block here. And then when the software detects that there is no more contact, you say, okay, your block has been placed. This is the first part of the project. The second part of the project is about reviewing the actual construction sites. So let's say you have used the software to lay down all your block. You could end up with a model like this, composed of two things. The point cloud provided by MESURIS. You can get there is a block over there. And the data of the model. If you look carefully, you can see that the blocks are not really aligned with the point cloud over there. There will be several answers. First one, the block could have moved during the pull-out phases of the placement, or it could have moved because we put block on it, so it moved. So one of the features of the software is finding the perfect position for that block. So if I take that block here, and I say compute optimal position, it will try to make the block fit perfectly to the point cloud, so we can find its actual position and orientation that you can have here. You can use this feature for the entire installation. I'm not going to do that because it could be quite long, so I will just show you the result, which is here. And you see here that block really are more really fits more on the point cloud. Okay. When you have that in mind, then you can use some tool to analyze your construction site. And one of the constraints you have is that you should avoid getting two blocks nearby which with the same orientation. So we build in a tool here that is the detection of such zone. For example, here we have 3 blocks with the same orientation. I'm going to stop the demonstration here because I want to show you some code. Okay. Now, just a word about architecture. We already seen the views on the demonstration. Just keep in mind this is a simple MVC pattern with views here. The data are stored in EMF model. Why? Because we really wanted to use all satellite technologies around EMF and build a DSL which is understandable by our client. And then we use EMF compare to synchronize all that. Because, as I've shown you in the video, the computation of the block, the actual position of the block, is asynchronous, so it doesn't block the US thread, meaning that you can have several threads modifying the EMF model. If you work a bit with EMF, you know that it's not really concurrent friendly, so you need EMF compare to synchronize all modification here and all read here by using exclusive or transaction to modify or read the model. Just a more advanced architecture came up, which is the same over there, but here we also display the network gateway we implemented with VertX, which is also an Eclipse project, a really nice framework that you should know, or at least look at it. We use that because it has really nice network library. It's reactive, so it matches our requirements, and it's really lightweight. And here you have the system provided by MESURIS. Which are the changes we faced? Unusual UI. So in the train, in the cabin train, there is no much space. So the pilot doesn't have a keyboard, and they have a really small screen, which is a touch screen. So we had to build such UI, and you can do it with Eclipse RCP quite easily. We talked about VertX, but to interface the many sensors, we use VertX, and it was really nice, and it saved us a lot of time. And low latency UI, we wanted to build a UI that doesn't freeze, and it's independent from the rate we receive data. So we make it in a way that we don't react to change of the model to change the widgets. Instead, we refresh the widget periodically. Other challenges, even if it was not really a challenge because the Eclipse Approach project already done it and it saved us a lot of time, we had to find a game engine written in Java that could be integrated into Eclipse, and that is JMonkey, which is a really nice game engine written in Java. Another challenge was scalability, because one of the projects we had to handle has more than 60 million points to display, so we had to implement some well-known 3D optimization techniques such as LOD for level of detail. Basically, it changed the level of detail depending on the position of the camera. And of course, be really careful on how we use EMF to make it scale properly. Security and licensing. One of the requirements we had from our clients that he wanted a really secure product, and because he wanted to be able to give license using USB physical dongle, we need a special product to do that. Moreover, he wanted something that couldn't be easily hacked. For that, he wanted to add jar encryption on each jar. So we use a really nice product called Meter, which helps you provide license, give you a license system, and secure your application. The plus is that it works well with Java and OSGI, which is not really often, and have a nice Java API, so we were able to build a Maven plugin, so the protection and encryption of our application was done in our continuous integration server. Concurrency is one of the main topics we had during this product, because we have several threads that can read and write the model, and we have the JMonkey thread that has its own constraints that we will see later. Okay, as it's not an open source project, I wanted to show you some code, so I've built another app that emulates how a forest grows, following some simple rule, and I will use that to demonstrate some of the problem we have. I will first show you the meta models we use, then I'm going to go really fast on how to integrate JMonkey in Eclipse. Then we talk about concurrency and how to display elements in the scene, and some testing. In our temperate climate, if you don't do anything on the land, it will go back to a forest state, following some stages. The first stages is the arrival of pioneer tree. This is the kind of tree that can grow from grass or nothing, and their main aim is to start to provide condition for other tree to grow, such as lightning or temperature. So I've made a simple meta model expressing those dependencies. For example, here we have two pioneer tree, which is a pine and an ash tree. Pine 1 provide condition for pine 2 and pine 3 to grow, and ash 3 provide condition for oak to grow. Let's see what the app looks like. Yeah, so the app is quite similar to the Blocksuite app. We have a project explorer over there that will display the model in live. We have a 3D scene over here that displays the forest, and here a property view. Let's define the constraints, the inputs of our simulation. We say, okay, I want that a year to be represented by, let's say, 100 milliseconds. So each 100 milliseconds a year passes, and I want to display at most 5,000 trees. Then I can start my simulation. So you can see on here that the forest is growing. I can navigate in the 3D scene here, and I have here the project displayed in real time with information from DMF. I can click on elements to display their property, and I can modify them. So here, each 100 milliseconds, there is 1,000 of action on the EMF model that are interpreted in my 3D engine. Okay, now let's use that to display some code. First, the meta model, we have three really simple concepts: a forest, a tree, and type tree. The trees are the real instance of the tree, and the type tree defines the characteristic of the tree, how they will grow, if they get diseases, and stuff like this. I'm not going to go to Eclipse for that because it's really simple. How to integrate JMonkey into Eclipse. First, you bundle the JMonkey into an Eclipse plugin, and then you use SWT bridge to display their frame into a SWT frame. The only important stuff you need to know is that this bridge is only available if you rely on the lightweight Java game library version 2, But if you start relying on the version 3, this bridge doesn't exist anymore, so you have to find other solutions to integrate into Eclipse. Other important information is that macOS deprecated OpenGL, so this kind of product may not work on Mac soon. Okay, so here are the key problems that we can have with this kind of products is about multithreading and concurrency. So here we have the 6 main threads that will be used in our application. The first is the Eclipse UI thread that could read and write on the model because there is a property view that you can read property and change them. You have the JMonkey UI that somehow should be aware of the MF model to build a 3D representation, and 4 other threads that will modify concurrently the model for different purposes. Okay, so first I'm going to display. I told you that to be able to modify or read the model, you should wrap all your access to the model using EMF transaction. So for reading a model, you will use this kind of code to wrap your access to the model. So we built a special interface doing that quite nicely. And to modify the model, exactly the same, but this time you create an EMF command and you run it on the command stack. Once you have done that, you need to create a renderer, at least the way we call it. Here is a tree renderer, which is responsible for displaying the tree in the scene and modifying their position and size and so on. So first, we needed to create a map that maps the semantic tree to the node, which is a JMonkey representation. And we've put that on an abstract app state, which is a basic component of the JMonkey application. Then we provided a model interpreter, which is basically a resource set listener implementation, which listens in post-commit and then interpret each notification sent by the EMF transaction framework. So for example, I want to add a tree when a tree is added. I want to add a tree to the scene when a tree is added to the model. So I will listen the feature here, say, okay, when the feature containing feature tree is modified, I will do something. Then I will catch the event add, and then I will do this code. So first, I'm going to build a representation for that node. Here is how I would do it. You create a node, and then you set its location, its orientation, and its size. When you have done that, you have to really think about when you want to attach it to the scene graph, because one of the main rules of JMonkey is don't modify the scene graph outside the JMonkey thread. So here we are in the thread that modified the model. So we can build the representation, but we shouldn't attach it here. Instead, we create a runnable and we enqueue it in a queue of the application that will do it later for us in the JMonkey thread. Now let's see the runners. So when you start the emulation, in fact, you start several threads. Each of these threads is responsible for modifying the model in its own manner. I'm not going to show all the implementation, but basically you have a child creation runner that is responsible for creating a subtree of a tree. So this is trees that are close to a parent tree. We have disease runner that gives disease or ill tree. And we have growing tree runner that we are going to look right now. So first, obviously, you need to wrap all your modification in transaction. And what this runner does, it iterates on all the model. And if the tree is not thick and it hasn't reached its maximum age, we make the tree bigger. If it's thick, it decreases the maximum age of the tree. Then, if it doesn't have reached its maximum age, I increment the age of the tree, or I remove it from the forest. So this is a quite complex modification because we have modification of the tree and properties. We have also pioneer tree runner, which is responsible on creating the pioneer tree on the map at random location. So each time this thread is called, it tries to define randomly if it should create a tree. If it does, it randomly determines the pioneer tree type, Then he creates a tree and verify if he can plant a tree on the random location, because we don't want two trees to overlap. So there is kind of a big implementation here. So these are the four main modifications that are done. So in the modification, we add, delete, and modify each model element concurrently. If I go back to the model now, the presentation, sorry, we're going to talk about tests, because we were doing this project using Agile methodology, and if you don't Agile project, you know that requirements can change really fast. So you really need a big test coverage to be able to react to those changes. So some basic knowing about JMonkey and I guess 3D engine in general. Scene is represented by a graph. If a node is attached to that graph, it's displayed. You have a scene root, then you have subnode, and the leaf nodes are geometry, which hold mesh and materials. Mesh are a bunch of triangles representing a 3D object, and material represents the way, the color, and lighting. So to test your app, you should just test this graph and see if your node is attached to it. Okay, how to test it now? First, you need in the setup to make a bunch of wait, because when you start initializing your app, you need to wait for it to be initialized before testing. So we use some countdown mechanism. And we need a way also to wait for modification to be rendered in the scene, because if you remember, you have a thread that modifies the model. The model is this modification send notification, then interpreted, and then we give it to a queue that will be run later to modify the scene. So if you want to test, you have to wait this scene modification. The test looks like this. You do a tree model modification, simple one. So I create a tree, I set its type, its location, and I add the tree to the forest. Then I do the modification, and using a special mechanism, I'm going to wait for the scene graph to be modified. Then I only need to check some property of my renderer, and even I can check if my representation of my tree belongs to the scene graph. If it does, it means that it is displayed. Thanks a lot for your attention. If you need more information on BlockSuite, please contact MESURIS or go onto the website. And if you need help to build your own 3D application on Eclipse, please contact Obeo. Thank you very much. Hello, everyone. Just before answering to your question, just let you know that the forest simulation app has been open source, so you can look at the code in the GitHub under Obeo organization. Okay, so I'm looking for question on the chat, but I can't see any. Okay, no question in the chat. So if you need, if you want to play a bit with the application we see on the second part of the video, you can go to the stand, the Obeo stand. We are on the exhibitor part of the Snapcard application. We can look together to the code and maybe play with the app. 25 minutes, really short to explain all the concepts that you need for building a 3D application. And so I guess you are welcome to come and visit us if you want to discuss on that matter. And if you want to know more about the application, okay, I will give the URL of the open source app, but if you look on GitHub, you search for the Obeo network organization. There is one repository which is called Forest Simulation, and the source is there. So you could look at there, or just send me a text message at the end of the talk, and I will forward you the application, the URL. Yes, that's that one. I didn't have much time to discuss the VertX uses we've made on the project because, again, 25 minutes is quite short. But the way we use it is to create the gateway to interact with the many sensors that MESURIS installed in the crane cabin. That really perfectly match our needs due to their really nice network libraries and their asynchronous model. So I would recommend to look at this library, and I wish I had more time to discuss more about that library or framework. Okay, maybe I can discuss one of the topic I didn't mention during the conference, during the talk, is about how you build your UI when you have many threads that modify really quickly an EMF model. Usually what you do is on each notification, you modify the widget to display the properties. But in our cases, the rates sent by the sensor was really high. So instead, we build a periodic UI. And for that, there is a really nice usability method that allow you to be called periodically. And we only refresh the UI periodically. And that was really nice enough for the needs of our client. Okay, so if there is no question here, you're welcome to the OBO stand if you want to discuss more on that matter. Thanks a lot, everyone. Bye.